Hello everyone, and welcome back to a new episode of Silicon Zeros. I want to start with, so again, just like I did with Multiply, I did Greater off camera. These kind of 4-star ones are often difficult enough to wire together that I don't really want to be doing them on camera. It's kind of like a long time where nothing super exciting is happening. I'm just like, where does this wire go again? So something I do want to talk about, I'll give you an overview of the Greater solution. And remember we visited Greater before and couldn't figure out a way to do it. So I'll tell you what realization I made that caused me to realize I could actually solve this at all. And then we'll talk some more about how the solution works. But first, I want to draw your attention to this bad boy. Ideal 22, but we did it in 18. So I was hoping when I got this the Steam key to this, that there would be some puzzle that I would beat what Pleasing Fungus thought was the best possible. And it took a long time, but we finally got one. This video, of course, is coming out long after the game was released, so I assume that he has since downgraded this 22 to an 18, or perhaps even something lower. But it's nice to be the first one, you know? I think for Manufactoria, I was the first one to find a couple of the what turned out to be best solutions. At least one, maybe more than one, I don't know. Insofar as like the official record was what was being kept on the XKCD discussion forums anyway. Like I don't know what was really the official record, but I never saw anything better, and people were competing and finding some pretty cool stuff. So I think I had a couple of those. Anyway, so what was the realization that I had here before we start looking in detail at how this is implemented? The problem that you'll recall I had was I said, let's try adding 1 to one of the inputs. I said, let's try subtracting 1 from A until it gets to 0. And in parallel, we'll try subtracting 1 from B until it gets to 0. And that's fine as long as both inputs are positive. But if any inputs are negative, then the one that gets to 0 first is actually the larger value, not the smaller one. And if they're both negative, then this never terminates at all. So clearly that was no good. And I was trying to think of some ways that you could, like, split this up by sign and, like, try 4 solutions in parallel, add 1 to A or add 1 to B, or subtract 1 from A or subtract 1 from B. And, like, you could do that, but even if you did that, the one that reaches 0 first wouldn't necessarily be the one with the right answer. You would basically find out which one was closer in cardinality to 0, but not which one is greater than the other. So you would still have some trouble there. And I think you could, from that, you could then apply some more specific addition, another loop to find out like whether the other one was the same sign or not, but that would be a tremendous amount of work, so I didn't do it. And what I realized was pretty simple, actually, is that we don't know the sign of either of these things, like whether they're greater than or less than 0, but we do know that at most, like if you add 1 to A and B is if you in a loop add 1 to A forever, either you will eventually reach B or A is bigger, right? One of those two things is true. And likewise, if you add 1 to B over and over forever, either you will eventually reach A or B was bigger. And so rather than using 0 as the terminating condition, what we should be doing is using the other number as the terminating condition. And with that realization, there were still some challenges in like actually wiring it all together, but the basic algorithm is relatively okay. So over here we've got sort of our standard blocking instruction decoder loop, I suppose you could say, where the counter is not strictly wired back into itself, but rather wired up into a selector that tells it whether it's okay to add one. And the source of this selector is, or the control wire for this selector is way over here, and we'll get to what that is later. But that's basically the done signal. I have found the answer for this instruction, please move on to the next one. In which case we add 1, otherwise we add 0. So that's pretty simple, right? And we decode the instruction we're looking at, and we get source. These are the two numbers to compare, and this is where to write the result. Now, the obvious solution, the one that I thought of first, was to, as soon as you read the instruction, save these two values into registers or latches or something, and keep incrementing both of them, and comparing back to these old values here, and see which one matches its partner first, right? Does source reach dest, or does dest reach source? Sorry, not dest, it's target. Source and target, target and source. And I got partway through that, but it was actually a little bit awkward. I forget why. I think in principle you could totally do it that way. But partway through I realized that I don't need to. What I did instead is I'm just reading these values straight off the decoder. I never save these anywhere. And since the decoder stays pointed at the same instruction until we found the answer, they're always there for me. And what I have here is instead, the only thing we're actually incrementing is a thing that I call diff. How much are we going to try adding to our two numbers? So rather than saying our numbers are 2 and 1, now our numbers are 3 and 2, now our numbers are 4 and 3. Instead, our numbers are always 2 and 1, and we're saying, let's try adding 1 to them. That didn't work, let's try adding 2 to them. That didn't work, let's try adding 3 to them. And so we only need to actually store a single number, which is the difference between what we're looking at currently and what we originally had. And this has the same kind of blocking counter as before, as over here. In fact, it's identical, I think? Except that the two control inputs are swapped, which is kind of... Or the two input values are swapped. And I guess actually this has a different thing being written here, maybe? Okay, so they're not quite the same, but it's the same structure of an adder that adds 1 to a latch unless the control signal says not to. Yeah, I guess that's the difference. This one adds 1 only if the control signal says it's okay, and this one adds 1 unless the control signal says you should reset. So this one is strictly increasing, whereas this one cycles from 0 up to n for some n, and then goes back to 0. But it is taking the same, if we look at this control input, it's going to here. This same control input is feeding both of our selectors on our counters. So great. We're storing the value we should be adding to x and y. And then what we do with these adders, I think, is pretty simple. Add the current diff to the value in source. And then compare that to the value in target. And that will tell you if source plus our delta is equal to target. In which case, we can say that source is at least as small as target, right? You added a non-negative number, possibly 0, to source and eventually reached target. Symmetrically, down here, we take the current diff, add it to the value in target, and compare that with the value in source. And if those two ever become equal, then you can say that adding a non-negative amount to target eventually yielded source, so target was at least as small as source. Now, I've been careful to say at least as small as, to make it clear that we can't make any conclusions about greater based just on, like, any one of these two things. We can conclude, however, that we have the answer. If either one of these outputs a 1, we know the answer, right? It's, I won't get yet to how we will actually compute the answer, but we have enough information. We've added enough values, enough of a big enough number to one of them to get the other, so we're done. So this comparator says, are either of these two other comparators equal to 1? If so, then send up the flag and tell everybody, get ready for the next number. Mostly, of course, that's these two counter values. We reset this one to 0, and we allow this one to advance. But also, there's this adder, which I'm particularly pleased with, which I got it wrong the first time. I had the general idea. So the question is like, okay, we need to write some value to the output, and it was a little bit tricky to figure out what that value should be based on these two things. I think, actually, if maybe I could do the same thing with do this with the same number of modules if I just use like 2 input selectors instead of an adder. Maybe it's a little bit tricky. I'm not sure how. I know Pleasing Fungus' solution uses like 3 input selectors in front of this writer, and I think you might need to do that to do sort of this if-else branching that you would have to do this way. But what I realized is that so what we're being asked is source greater than dest? And this is true only if dest is at least as small as source, right? It's smaller or equal. And also, it is not the case that source is less than or equal to target. So what we can do is take the numbers output by these comparators and add them together. If the value that we get is 0, then, sorry, not these two adders, because when you add them together, you can't tell what the result 1 means. It might mean only this one is on, or it might mean only this one is on. And of course, from that, you can't figure out the answer. But if you add together this one, which is whether either one of them is on, with this one, which is whether this is on, then you actually can figure out exactly what you need to know. Specifically, if the value is 0, then, of course, nothing has been found. If this were 1, then the answer couldn't be 0. And if this were 1, then this would also be 1. So if either of these is 1, then this is non-zero. So if we find a 0, we can't write anything, we don't know the answer. But if the value is at least 1, then this is definitely on. If the value is exactly 1, then we know that only this is on and this isn't. Because if so, if both were on, we'd be getting a 2. And it's impossible for this to be on and this not to be on. So we know exactly what the answer 1 means, which is that this is on and this is on. And we know that the answer 2 means that they're both on. Or, well, it means that this is on and this might be on, but we don't actually care. It's a little bit tricky to walk through the Boolean algebra out loud, but if you'd like, I encourage you to pause the video and think about, in the case 0 is obvious. 1 means that this is lit up, but this is not. Therefore, this is, which means that, what? Target is at least as great as source. No, is that right? Shoot. It's no, it means target is smaller than source because we added something to target and got source. At least as small as. And since this one isn't on, it's in fact strictly smaller. Target is strictly smaller than source, which means we can include greater, and we write a 1. If this is on, we're getting a 2, which means that both of these, or not both of them, but at least this one turned on, which means that we were able to add something to source and get target, which means that source is at least as small as target and therefore not greater than it. So that's the whole thing. I'm pretty pleased with this solution, and we'll just watch it run here for fun. But it sort of does pretty well. You know what? Actually, let's stop and do it tick by tick a little bit. So on this first tick, we're saying is 2 greater than 1, and so we're first trying to add 0. So hey, maybe they're the same. In which case the answer would be false. But they're not, and so we allow this counter to tick up, but not this one, and we continue. Now we're trying to add 1, and we've determined, hey, if you add 1 to, what is this? Target, then you get an answer which is equal to source. Therefore, target is smaller than source. Or at any rate, target is at least as small as source, and because this one isn't also equal, they're not the same. So there you go, we're writing this. And something, and anyway, and so this ends up like, it just sort of does, then we test the opposite, and that still works, and we test some numbers that are quite far away, and we get all the way up to 10, and then we say, hey, look, we added 10 to -5, and we got 5, so, okay, so it all sort of works convincingly. The last case to test is just the one here that does it work on 2 numbers that are the same. And the answer is yes, because we do try 0 at least once. And find they're the same. These both light up. The output of this is 2, and we say, nope, no good. It's so weird. Even now, it confuses me, like, why isn't the answer ever 3? It's because we're not adding together 2 bits that are independent, right? We're adding together 2 bits. This is either 0 or 1, and this is either 0 or 1. But we're just adding them, right? We're not doubling one of them and then adding them together, which is a way we could get, we would get 4 possibilities. But actually, since they're not independent, it's impossible for this one to be 1 and this one to be 0. So there's really only 3 possibilities: 0, 1, and 2. And they anyway, so great. What an exciting puzzle. I had a lot of fun with it. Sorry you guys didn't get to see it, but I hope you enjoyed the explanation. I looked at Pleasing Fungus's solution, and first of all, it has 23 modules, not 22, so I'm not sure what the deal is there. Whether someone other than him found a better solution that he encoded as ideal, or if he just miscounted something or what. But, so something I like about this solution is that we don't actually buffer anything. Every single step, we're doing a useful calculation, right? On this, if the very first input is 2 numbers that are equal, we are able to write... Does that ever happen? We are able to write out the result that its source is not greater. So yeah, here. So this test is a fun one, I guess. We say right away, write out a 0. So we don't waste any time buffering stuff to save for later, as you might if we had like if we had, say, a register or a latch to store the current values of x and y, and added 1 to each of those every time, then the organization gets a lot more complicated of like, how do you manage all these things, make sure you wait long enough to load the old value in before you start adding. So what I really like about this is that 0 is the correct value to start with for both of these latches, and we get them both reset in the same same tick that we're writing output. We get these back to a good value to start on the next one, so that we never are waiting around for anything to happen. I think if they were measuring ticks, this would be an optimal solution in terms of ticks, right? We're given 168. It takes us 79. Anyway, so I'm quite pleased with this solution, and particularly pleased to be doing it better than was expected. You know, it's partly just because I'm playing this before anyone else, right? If I were, I'm sure I wouldn't be the only one to find this solution. But it's nice to have found it before Pleasing Fungus or any of his other playtesters. So there, I'm very smart. Okay, puzzle complete. Alicia confuses me. She says she's only here for the money, and unlike the rest of us, she leaves at 5 sharp every day to have dinner with her husband. But she's working here, not at a big company that could give her a bigger paycheck. And while she's in the lab, she works so hard and so well that she puts the rest of us to shame. It doesn't add up to me, but I'm sure she'll appreciate her brand new grater machine at least. Yeah, work-life balance, I guess. Like, it's good for you. There is a place for people who put in, you know, a whole bunch of hours, and that's great. But I think that usually those people are the ones with a ton of stock equity. And for most companies in startups where people are working super hard, the stock ends up being worth nothing anyway, so it's sort of a gamble. But anyway, I digress. What are we going to do with the rest of this episode? We spent a lot of time just looking at a solution to Grater. I think that now is a good time to work on something smallish in size, branch. The other one that we're waiting on is Delay Jump. I think 3 stars is a bit ambitious for the end of this episode. I had a look at Reg Hazard. It seems hard. It's just basically handling more instructions and having to deal with writing to registers in the middle of a pipeline that has potentially already loaded the old register values. Sort of the same thing as we've already done with memory, but now you have to deal with it with registers as well. Whereas branch should be pretty simple, I think. In fact, let's grab our jump thing here. I'm sure we're going to need something very much like this. Branch. So, flow control. Choosing instructions to execute based on the current state of the machine. I think I can sort that out. Execute all instructions. So if we look over here, we have jumps, set ours, add ours, save. Did we have all of these in our jump thingy? I don't think so. We have more kinds of instructions than we've had to deal with before in here. That's a bit of a downer. Well, not a downer in the sense that it's making me sad, but in the sense that, like, this is not going to be a quick puzzle to just sweep under the rug on the way out of this episode, is it? Our goal, we're going to overwrite this with 70. How exciting. Okay. So the problem is, right now, let's go look again at jump. It has to deal with set R, add R, save, and jump. Oh, maybe we are handling all those then. And we just have to handle set R, add R, save, and jump. And what do we have to deal with here? Set R, add R, save, jump, and branch if equal. Okay. Yeah, no, we actually do have everything except branch already implemented. Alright. It just looked like we were missing more things because I looked at this and, like, there's so few things actually filled in. But that's because this particular operation selector only needs to do anything in a couple of cases. So basically, we are doing something quite similar here, I think, to handling right. This is not a we don't have to worry about pipelining here, which is going to make things much simpler. That's why delay jump and in the main pipeline, in the main storyline, is going to be quite a bit harder, I think. Having to flush the instruction pipeline when you run into a jump is part of what makes jumps hard, and why like conditionals are so slow in modern computers. Like I mean, they have branch prediction, so I hope we don't have to implement branch prediction. Good heavens, I don't think we do though. Okay, so all we really have to do, I think, is each of these is already empty for jump, and we're basically going to treat branch if equal the same as jump, except that this, instead of wiring this up to this, we'll wire it up to some stuff that tests some registers or whatever. So what are the arguments to branch if equal? If registers 1 and 2 are equal, fine. So that's a little bit trickier, I think. Oh, maybe it's not. Haha, it's not, of course, because this is already being fed by target, the register in target, and this is always being fed by the register in source. And those are the things we branch equal based on. So we can just take the output of these two registers, and it'll be the things we're supposed to compare, right? So what we need then is an input selector in front of this in the branch if equal position. And what it should read is this. Hang on. It will also need a comparator, like so. Actually, let's put the comparator over here. No, that looks ugly. Let's put it over here. Taking this and this. Hello? Gimme? This. If the two are equal, then we will jump to the address in destination. Otherwise, we will take this value and put it here. And I think that's it. Right? Notice, interestingly, when I moused over this, you can see all the places that we might be adding one to the instruction pointer, I guess you might say. In every case except jump, there's a possibility that we'll add one. In branch equal, it's possible. In the other three, it's certain. And this is the other address. It's just jump to a specific slot, right? Yeah. Okay. Great. Well, let's test it. Although I'm pretty confident. We'll do setar. Yeah, that's fine. I'm sure setar is fine again. We've written a 30 and a 40. We're now about to add them together into a 70. How lovely. And now we say if 1 and 2 are equal, which they are not. Uh-oh. Did I do it backward? No, I didn't. This 4 is coming from up here, which is exactly what should be happening. We're just advancing past this instruction. Now we encounter a 4, which says jump to 40, so that's what we're doing. Good. Set our, instruction 5 to 70, okay. And now, the interesting one, I think. We say, are registers 2 and 3 equal? Well, it turns out that they are, and we are therefore jumping to slot number 30. And that is what's happening. Very good. Slot 30 says save into memory slot specified by 3, which is 70. No, wait. Save into the memory slot at 0, which is 30, the value from register 3, which is 70. So we're going to write I'm sorry, wait, where are we? We're at this save. That's 30. We're about to write into the slot specified by 0, which is 30. Ah, of course, the writing is happening here, not in the register. That's what I was confused by. So we're writing a 70 into slot 30. Ta-da! I'm a little bit puzzled, because I guess we eventually got the memory to the goal. It just feels a little bit weird, because, like, shouldn't we then do instruction 31? But, like, there isn't one. I don't know. A bit weird, but okay. Alicia will be pleased to see this, I think. Pretty sure this is just what she was asking for. In college, I wasn't sure what to study. I went into hardware engineering for a few reasons. It was fun. I was good at it. No, I should be pronouncing this differently for the semicolons. It was fun. I was good at it. It seemed like a growing field, and I felt like I could help others with my work. Sometimes it's hard to tell how much impact I have on the outside world, but I'm helping my friends here. That's enough for me. I just had this thought. This is empty, which I assume is, like, to mean, hey, this is me. And then I thought, should my Steam picture be here? Like, that would be a way to say, hey, this is you, by the way. But then I realized, like, actually, maybe my Steam picture is here. I don't think I have a Steam picture. So maybe, you know, maybe for everyone else this does look like your Steam profile, and I'm just an idiot for suggesting this. But it's an interesting idea. I don't know if you would want to do that, but something you could do. Okay, well, that was fun. Simple enough, I guess. The first one, I think explaining Grader was more fun than implementing branch. But I don't think we certainly don't have time to implement full CPU in this episode, but I'd like to have a look at it and see what it is we have to do. I'm pretty sure I've set up all the register instructions. Add, load, jump, branch. Time to put them all together. It's late enough that I'm getting bleary-eyed. I need to finish this before I collapse. So I think the only thing in here that's new is load, isn't it? Or actually add M maybe is in here, which we haven't had before. We have add R, or we've had before, but not in this sort of sequence. Okay, looks like there is no add M. We don't add memory slots together anymore, like barbarians. Interesting. Well, this shouldn't be too bad, but I'm still not going to do it, and I guess that's why it's only 2 stars. Still not going to do it in this episode. We'll probably do it as a warm-up for the next episode, and then move on to something a little bit tougher in the main storyline, if such it can be called. Thanks for watching, and I'll see you next time.